One, two, three. One, one.
Good morning, everyone. Welcome to the morning session of this very exciting meeting. This morning we'll have some really interesting talks, starting with Jonas Smith-Sinas, and he'll talk about kinetic inductance detectors. Welcome.
Well, thank you very much. Thank you to the organizers for the opportunity to come and visit. It's been a very interesting meeting so far, and also thank you very much, Aliyah, for all of your efforts on my behalf. I very much appreciate it. So today I'll be speaking a little bit about kinetic inductance detectors. You heard Bruce mention them a little bit yesterday, so I'll be going into some of the details, and I think you'll be hearing even more later today. I'd like to mention, of course, this work that I'm going to describe is not just my own, but a significant number of people contributed, as you can see here. But before I get to that topic, I'd like to start with a little bit of history, going back to 1965. You can see in this nice picture in the upper left, this is President Lyndon Johnson being given a photograph by Bill Pickering, who at the time was the director of the Jet Propulsion Laboratory in Pasadena. It's a photograph of the surface of Mars taken by the Mariner 4 spacecraft, which flew by Mars and had a television camera aboard and took these pictures. Some of the other people are notable. This is James Webb, who the telescope is named after. He was the NASA administrator at the time. This guy, Jack James, was the JPL project manager. This guy, I forget his name, but he was in charge of science, I think, essentially at NASA at the time. So this was a big deal. And the person who was responsible for the instrument, the TV camera that took those pictures, is shown here. His name is Bob Layton. He was the principal investigator of that instrument. And if you look at some of these other names, some you'll recognize. James Van Allen, of course, from the Van Allen belts. There's another name here that you won't recognize by the name of Vic Nair, who with Bill Pickering and Bob Layton had something in common in that they were essentially all academic descendants of Robert Millikan. Millikan was interested in cosmic rays, and Bill Pickering was his graduate student in the 1940s, studying cosmic rays using balloons. And Pickering's specialty was actually getting the data back down from the balloon by telemetry, which made him somebody whose skills were needed at JPL. That's how he became director. So anyway, this was 1965, so we celebrated the 50th anniversary of this event a few years ago. And then Bob went on to have a very interesting career. One of the things that he did was to really open up the field of infrared astronomy, particularly with this instrument that you see over here. This was the telescope that Bob built to perform a survey of the infrared sky at 2 microns from Mount Wilson in Pasadena. And this really discovered a lot of infrared bright objects and really was a big boost to the very young field of infrared astronomy at the time. And a number of notable people participated in that project. One passed away quite recently by the name of Jerry Nelson, who was responsible for developing the designs that were used in the Keck 10-meter telescopes, the segmented telescope design. So you can see his influence from Bob Layton. Well, another thing probably many of you know is that Bob's name appears on the Feynman Lectures of Physics. So Bob and Matthew Sands were actually responsible for getting these lectures put together after Feynman had delivered them to the freshman and sophomore classes at Caltech. So by the late 60s, early 70s, Bob had become interested in millimeter wave astronomy. This was a brand new field that was just opening up. Probably the biggest event was the discovery of the rotational emission from carbon monoxide at 115 gigahertz, or a wavelength about 3 millimeters, in 1970 by the Bell Labs team, which included Arno Penzias and Bob Wilson, who in 1965 had discovered the microwave background. And so this was clearly going to be a very interesting field, and Bob Layton started working on developing telescopes, as you see here. He's in the process of building a 10-meter telescope to do millimeter astronomy. These telescopes, a number of them were built and deployed here in, you can see in a high desert in California, not far from the Owens Valley. This was called it was originally called the Owens Valley Millimeter Radio Interferometer, became known as CARMA when it joined forces with a group from Berkeley. And it's this early development of the field which then led to the construction of the ALMA interferometer on Chile, which I think many of you know is the largest single investment in ground-based astronomy in the world at about $1.4, $1.5 billion. It's an array of some 60 dishes, each of them 12 meters in diameter. And this project essentially was made possible by the early efforts of people like Bob Layton. Well, one of the things that Bob knew would be needed to go with his telescopes were sensitive receivers. And that led to the hiring of this man, Tom Phillips, from AT&T Bell Labs. Tom was a solid-state physicist. He was studying properties of materials at low temperatures, and he heard a lecture at Bell Labs from Arno Penzias about the discovery of carbon monoxide. And Tom found the lecture quite interesting, but there was something that was puzzling him, and that was the receiver noise that Arno was describing was measured in thousands of Kelvin, and Tom couldn't understand why it needed to be so high. And so he went up after the lecture and he asked Arno, why is your receiver temperature so high? Why is it thousands of degrees? Why isn't it room temperature, 300 Kelvin, or why don't you cool it to 4 Kelvin and have it be 4 Kelvin? And Arno didn't quite appreciate this question and said, Tom, if you think you can do better, why don't you? I think he was a little angry. And so that's how Tom became an astrophysicist and decided to do exactly what Arno had challenged him to do, develop better receivers. And so you see the instrument that Tom is working in is a receiver of the type that he invented while at Bell Labs using superconducting tunnel junctions as the sensitive element. And it's this technology which makes ALMA possible. This is the fundamental technology which is used to build the ALMA receivers, which you can see here. The 10 bands here, you can see one of the cartridges. the horn that receives the radiation from the telescope. This came from Tom Phillips's invention, along with Paul Richards at Berkeley. So Bob Layton was well connected at JPL, as you saw. He had been principal investigator of this television camera experiment on Mariner. And so when he was developing these millimeter wave telescopes, it was obvious to him that one interesting use would be to put one of these telescopes in space. And so you see this interesting image of one of Bob's telescopes springing out of the cargo bay of the space shuttle. The space shuttle was being developed, and it was promising transportation to space with very low cost. Of course, that didn't happen. But nonetheless, this is the kind of idea that Bob was thinking about. And in fact, this project, this concept of having a large millimeter, submillimeter far-infrared telescope in space was reviewed in the US by the decadal survey process. This is the process by which big astronomy programs in the United States get prioritized every decade. And so you can see it got on the list, but it was at the bottom of the list, which meant that it didn't, of course, happen. A smaller project, the ground-based version of Bob's telescope at a good site for shorter wavelength work in the submillimeter, did get recognized by the survey. And as a result, that project actually went forward and got built. There was a version of Bob's telescope which was built on the summit of Mauna Kea. Here you can see it. It's the Caltech Submillimeter Observatory. You can see the dish under construction, and Bob and Tom Phillips shaking hands at the dedication some 30 years ago. And meanwhile, in terms of the space project, that moved along. JPL got involved in doing studies for NASA. Eventually, you saw pictures that look something like this. You can see the shuttle. It's no longer coming out of the bay, but there's some kind of a space station, and it's being assembled. And to give you a sense of scale, that's 20 meters now. It's not 10 meters anymore. And then even more scary is there's the astronaut who's busy assembling this thing. And it quickly got to the point of being far too large to be affordable. And it eventually, in the early 90s, funding for this kind of study was stopped. But meanwhile, Tom knew that this project had gotten too large and was starting to propose smaller projects. So here you see a 1986 proposal for something called the Submillimeter Explorer, a much smaller spacecraft to start doing work in the submillimeter and far infrared from space. And after many proposals and a lot of work, eventually cooperation with the European Space Agency led to the U.S. participation in the Herschel Space Observatory, which you can see here was launched in 2009 and was quite successful. Okay, so I was a student at Caltech, an undergraduate student, at the time that Bob Layton was finishing up these dishes. In fact, I took a course from Bob as a freshman. I was still at Caltech at the time that Tom Phillips was hired onto the faculty, but I wasn't really aware of these activities. I left Caltech, I finished, I went to Berkeley for graduate school, and it was at that point that I got involved in submillimeter astronomy, as you can see here. That's me. This was a splinter group of the larger group that was led by Charles Towns. Al Betts, my research supervisor, was a former student of Towns, and we were doing laser spectroscopy in the submillimeter from this airplane, from the NASA Kuiper Airborne Observatory. And we were able to detect features, spectral lines from carbon, both neutral and ionized fine structure lines. But we were using the same type of receiver that Penzias and Wilson had used in their CO discovery. And instead of our noise temperatures being measured in thousands of Kelvin, they were measured with 10,000s of Kelvin. It was really difficult to detect anything, and it was clear that we needed better receivers. And so as a postdoc, I decided to go into this field of superconducting detectors and receivers. I went to University of Illinois to do my postdoc, which you can see was quite different than California. And I worked with two people. One of them is Fred Lowe, who was the director of the National Radio Astronomy Observatory while ALMA was being constructed. He unfortunately passed away fairly recently. And I started working on these superconducting detectors that Tom Phillips had developed. Another person that was there was a professor in electrical engineering by the name of John Tucker. And he had, while working at the Aerospace Corporation in the early 70s, had become interested in the question of how sensitive could a receiver become if it was using a diode for detection. And in particular, he was thinking about diodes in which the electrons tunnel quantum mechanically. And he developed a theory which ultimately showed that such devices could reach the fundamental quantum limit of sensitivity. And as a result, these were quite interesting. And so you can see some of his equations in his own hand, leading to the conclusion that in such a device you essentially get one electron tunneling for every photon which is absorbed. It's really a quantum device. And I got to know John at Illinois, and he told me a story about how he ended up at Illinois. While he was working at Aerospace Corporation, most of the people around him apparently didn't really understand what he was doing, didn't understand his theory and so on. And John Bardeen happened to be on the visiting committee, so they asked John Bardeen to go listen to what Tucker was doing. And so Tucker gave him a long presentation, and apparently that went okay. And a few years later, John Tucker got a phone call. He picks up the phone, and the person at the other end says, "Hello, this is John Bardeen." And Tucker thought that this was a joke. It was one of his friends, you know, trying to pull his leg or something. And so he said, "Yes, and I'm the King of England." Well, it really was John Bardeen inviting him to come to Illinois for an interview. So that's how he got on the faculty. So I got into this business, and I moved to Caltech around 1990 and started flying these superconducting receivers again on the Kuiper Airborne Observatory. You can see one of our instruments, liquid helium cryostat, behind the telescope. And this kind of work, development of this technology, ultimately led to our contributing these detectors for use on the Herschel Space Observatory. So here you can see one of the devices that we delivered for that project, and some of the details, and those two little dots are the superconducting tunnel junctions that are the detectors. Well, around that time, in the mid to late 90s, I started to become interested in not doing necessarily spectroscopy, but doing imaging in the submillimeter and far infrared. And there was this interesting prospect of detecting galaxies that were bright at these wavelengths. It had been predictions dating back even to the 1960s that might be possible. And finally, this instrument called SCUBA, a companion telescope on the same mountain on Mauna Kea, but this is a United Kingdom, Canadian, and Netherlands project. With this camera, as you can see here, a total of 37 detectors managed to make an image. And this object that you see here, which is rather bright in the submillimeter, turns out to be a galaxy at a quite high redshift, at a redshift of over 5. And that was only discovered, as you see here, in 2012, some 14 years after the discovery. And the problem in determining the redshift is that the object is completely invisible in the optical, as you can see here. The image in the background is taken with the Hubble Space Telescope. The contours show you the submillimeter detection, and although the object is extremely bright in the submillimeter, it's invisible to Hubble. And obtaining the redshift means you have to take a spectrum, and if you can't see the object in the visible, it's very hard to take a spectrum. And so eventually the spectrum was measured not at visible or infrared wavelengths, but at millimeter wavelengths. And so this is the kind of thing we were getting interested in doing. And you can see it's a fairly crude detector array. And it was clear that you would need larger arrays. And so with some struggle, larger arrays were built and flown on Herschel Observatory. And here you can see an image of the sky. And each one of these little dots is one of these submillimeter bright galaxies. And so you can see the sky is completely populated with these submillimeter bright galaxies at cosmological redshifts. And there's quite a lot of interesting work to be done. But you need better detector arrays. You need larger detector arrays. And so in the late 90s, we started thinking about how to do this. There were ideas that were being proposed, starting to be worked on. You heard them mentioned, the so-called transition edge sensor bolometers, which use a superconductor operating on the superconducting transition. But in our opinion, these devices seem to us to be more complicated. There were a number of issues that, as experimentalists, we weren't very happy about. It seemed too difficult of a way to make large detectors. And so we started thinking about other ways to do it, which led us to the development of kinetic inductance detectors. And so here's a photograph of one of our detector arrays. There's 500 pixels in this array, and the key point is that there's only 2 electrical connectors, and the entire array is read out through those 2 connectors, and it's a rather simple device. At the same time, it's quite sensitive. So there are many, many ideas in the literature that you can find about how to make superconducting detectors. Here's a fairly early example, but the physics involved here is not so different from our detector, the kinetic inductance detector. And critically, what you see here is that a photon is coming in, is being absorbed in the superconductor, and is breaking a superconducting electron pair, a Cooper pair. In this diagram, that's illustrated in the so-called semiconductor picture, where you see an electron in a hole being created by the photon being absorbed, and the electron can tunnel across a barrier, and then that gives you a current, which you can measure if you apply a bias voltage. So with this kind of device, any photon which has enough energy to produce this process to break at least one superconducting electron pair should in principle be detectable. And so that means that the energy of the photon has to exceed the superconducting electron gap. And the gaps are usually quite small. They're measured in millivolts or even fractions of a millivolt. So this means you can make this kind of detector work in the millimeter or far infrared. And this kind of device received quite a bit of attention starting in the 1970s, throughout the 1980s. But one of the critical missing aspects was there was no way of multiplexing these detectors, no way of reading them out in a simple way where you could have many, many detectors read out simultaneously. And so making large arrays was essentially impossible. And so we were thinking about how to use this same basic physics, but come up with a different way to read it out. So here you see the same kind of thing, a photon coming in, breaking apart a superconducting electron pair, leading to individual electrons. And one of the things, one of the properties of superconductors is that at any finite temperature, you can have both superconducting electron pairs, and at the same time, some fraction of those superconducting pairs will be broken. They will be broken into individual electrons. And both of those can carry current. Both the pairs and the single electrons can carry current. The main difference is that the superconducting electron pairs do not scatter. They carry current in a lossless fashion, whereas the single electrons do scatter and they contribute resistance. So in terms of an electrical circuit, if you think about current flowing through a superconductor, you can think of it as a very simple parallel circuit involving an inductor and a resistor. The inductor represents the current that's being carried by the pairs. The resistor represents the current that's being carried by the individual electrons, and those individual electrons can scatter, and therefore they have an ohmic resistance, whereas the pairs do not. And so the idea is that if a photon comes in, breaks a pair, you will change the inductance because there are fewer pairs. You will change the resistance, and if you can measure that change in the total impedance, you can have a detector. Now the problem is that if you calculate the fractional change in this inductance, as you might expect, is proportional to what fraction of the superconducting pairs you're breaking. And this fraction, if you want to have a sensitive detector, will be very small. And so you have the task of detecting a very small change in this inductance. And so how can you do that? Well, there were various ideas that were put forward to use squids, very sensitive ammeters, essentially to measure the change of the current flowing through the inductor. But another option is to use a microresonator to put this inductor into a resonant circuit and then measure changes in the resonant frequency. And then it's quite easy to measure rather small changes in the inductance. And so that's what we did. And so here's an example of how one of these detectors might look. You see a meandered strip of superconducting metal. In this case, it happens to be titanium nitride. And this strip is just being meandered, so this is forming an inductor. And then down here, you have a set of fingers which are interdigitated, and that structure forms a capacitor. And so the combination of this inductor and this capacitor forms a resonant circuit. In this case, the resonance frequency is about 1 gigahertz. The overall scale size, as you can see, if I get that here, is about 1 millimeter in size. And then you send a signal along a transmission line nearby, which can excite this resonator and interact with the resonator. And by measuring the transmission of the signal past this resonator, you can sense the resonant frequency of that structure. And so, as I mentioned, for this device, the resonance frequency happens to be about 1 gigahertz. And the other trick that you can play is by choosing the geometry of this meander and by choosing this material, you can make this area be a fairly efficient absorber in the submillimeter of far infrared. So you can actually illuminate this area with submillimeter of far infrared photons and absorb them, which you need to do to make a good detector. And so here's the result of a simple detection experiment where you illuminate this area with radiation from a black body whose temperature is being changed from 10 Kelvin to 40 Kelvin. And as you change the temperature of the black body, you can see the resonance frequency shifting down. That's because as you change the temperature, the photon rate landing on the device is going up. You're breaking more and more of those Cooper pairs. That actually drives the inductance up. That shifts the resonance frequency down. You can also see that the resonance is becoming shallower and broader. And that's because you're also simultaneously changing the resistance. You're producing these single electrons. And those single electrons, that extra ohmic dissipation is spoiling the quality factor, the Q, of the resonator. So you can see both of those effects, and both can be used, at least in principle, for detection. And if you look at these, if you look at this frequency axis, you can see that you're getting shifts of order 10 kilohertz, and as a fraction of the resonance frequency of 1 gigahertz, you're talking about a part in 10 to the fifth. And you can see it's very easy to see that shift. In fact, you can see a shift which is a small fraction of the line width. Let's say a part in 10 to the fifth of line width is not hard to do. And so that's how you get a sensitive detector. Now, if you look at the electrical behavior of the superconductor in a little more detail, you can appreciate the several things that are going on. So what you see here plotted is the surface impedance, the imaginary and the real part. So the imaginary part is the surface reactance, the real part is the surface resistance. And you can see that there's a big feature here, right around 100 gigahertz. This corresponds to the gap energy of the superconductor. So at frequencies below the gap energy, the superconductor behaves like a superconductor. The impedance is dominated by the reactance, and the resistance, as you can see, is 5 orders of magnitude smaller. So at these frequencies, you can make a very good resonant circuit. But above that frequency, above that gap frequency, in essence, the superconductor no longer behaves like a superconductor. It behaves like a normal metal. The photon energy is too high. The superconducting electron pairs, in some sense, can't keep up with that high of a frequency. On the other hand, that's exactly what you need to have a good absorber. So at the optical frequency or the optical wavelength, you're making use of the fact that the superconductor essentially behaves like a resistive metal. At the readout frequency, you're making use of the fact that the superconductor behaves like a superconductor. It has a very high quality factor. And so now, in order to be able to make a large array, if you have a bunch of resonant circuits, it's not very difficult to make multiple copies of them, to design them each to have a different resonance frequency, and then send readout waveform, which is a superposition of the various frequencies needed to excite the various resonators. And then over here, this represents the input of an amplifier, which is then being used to measure what's happening with all of these resonators simultaneously. And so here you can see, as a function of frequency, the various resonances that we get in one of these arrays. There's some, as you can see here, over 400 resonances packed into this frequency range. You can see that the array was designed to have 432 resonators. We see 415 of them, so we have a rather high yield in this particular device. And this is not unusual. This is fairly typical. And what controls the yield is the ability to keep these frequencies separated. We can't control them with perfect precision. There's some random variation that occurs as a result of the fabrication. You can't control the geometry perfectly. You can't control the film thickness perfectly or the critical temperature, etc. And so there's some scattering. There's some random motion of the resonance frequencies, and it's possible for two of them to collide and essentially overlap in frequency space, at which point you've lost both of them. You can't read them out independently anymore. And so this shows you that collision probability as a function of the quality factor of the resonator, and it depends on how many resonances you're trying to pack into a given frequency range, let's say an octave of frequency range. And the way that you get denser multiplexing is simply to use higher Q resonators. That makes them narrow in frequency space, makes the collision have low probability. And so you can get rather high multiplexing by using high Q. Now, in terms of the readout electronics, it's not so difficult these days either to do this. The basic idea is to generate this waveform that has all these different readout frequencies simultaneously. You generate that digitally. You use a digital to analog converter. It has to be fast in order to produce the bandwidth required. Once you've generated that analog signal, you send it past your array. It gets amplified in the cryostat. It comes out. You digitize. And then you need to perform a Fourier transform to separate the frequencies, which again you do in real time. These days it's not so difficult. You can use a field programmable gate array program to do Fourier transforms, or you can use a GPU, a graphical processor unit. Both of these will work. And then you pick out the channels in the Fourier transform where your detectors sit, and you throw the rest of the channels away. And so here you see a system that uses the FPGA. It's located over here. Here you see a system that uses a GPU, which just plugs into an ordinary computer. It's no longer so difficult to do this. So there's a variety of resonator structures you could use. You can use a structure of the type that I showed with this meandered inductor and interdigitated capacitor, a so-called lumped element resonator. You could also use a transmission line resonator, which you see over here, a quarter wavelength section of transmission line coupled to a readout line. Both types can work. Both types have been used. In fact, we started out using the transmission line variety in our initial work, which you can see over here. This is a so-called microstrip resonator where there's a superconducting ground plane, there's a layer of dielectric on top, and then there's another superconducting strip on top. So it's the sandwich of the ground plane, the dielectric, and the superconductor that forms the transmission line. And you can see we measured this nice high quality factor around 40,000, which gave us confidence then to start actually taking this seriously and pursuing this idea. So this would have been around 1999, 2000. But one of the things that we discovered fairly soon was that there were interesting and unusual behaviors of resonators of this type, which we really didn't understand. There were interesting nonlinear behaviors, power-dependent behaviors, and as a result, we abandoned this particular geometry and we moved to a geometry called the coplanar waveguide, which looks like this, in which the entire transmission line is formed from a single layer of metal deposited on a high-quality substrate, usually silicon, or it could be sapphire, something like that. And then you form the transmission line simply by etching gaps where you need them. And because this structure avoids the deposited amorphous dielectric, there's one less material that you have to worry about. It's a simpler device. And it allowed us to focus on just the properties of the superconductor instead of having to worry about what the dielectric was doing. Well, that turned out to do the trick. That gave us quality factors that were much higher than we had seen before. You can see quality factors of order 10 to the 6, even higher in some cases, and now is made using aluminum, and you can see it's simply the aluminum film is being etched, and this little gap here forms a capacitor. So essentially the microwaves are just bouncing back and forth between the ends. It's very much like a Fabry-Perot resonator. And with this simple device, we were able to get very high quality factors. And then the next experiment we did was to illuminate these with X-rays, 6 keV X-rays, and a single X-ray produces this beautiful pulse. You get many, many Cooper pairs being broken with a 6 keV X-ray and a millivolt binding energy for the Cooper pairs. You get millions of Cooper pairs being broken, and so that gives you a nice strong signal. And from the height of this pulse, the detector response, you can measure the X-ray energy quite nicely. And so you're absorbing them. So in this particular test, this was simply a proof of principle. So the device was not designed to be a good detector. We simply flood illuminated the whole thing. There was an X-ray source placed nearby, and the X-rays could be either absorbed in the ground plane, in the center strip of the resonator, or in the substrate. And so you see a variety of events. And by selecting the events with the highest amplitude, you can pick out the events that correspond to absorption in the center strip. And it's those events that give you pulses that look like that. And so this led to our first paper on this detector. And then that's when we started to try to seriously develop these for real applications. And one of the things that was true was that the quality factors that we were getting were very much higher than had previously been shown for superconducting microresonators. This shows you a survey of some previous work, and you can see around 2000 when we started doing the work, all of a sudden the Q went way up. And this was simply because as we started to work on these resonators, we started to understand what some of the problems were that had previously limited Q, and a big problem that had limited Q up to that point was simply the dielectric, was losses in the dielectric, which hadn't been appreciated. There were other issues as well, but that was one of the main ones. And so one of our former students, whose name you can see here is Rob Scholkopf, came to visit our lab, was very interested in what we were doing with these high Q microwave resonators. And he was interested in using one of these resonators and coupling it to a superconducting qubit. And so he did this experiment, the so-called circuit QED experiment, which was published, as you see, a year later. This has now become a quite famous paper with many thousands of citations, and it basically sparked a major change in what was happening in the superconducting quantum computing experimental work at the time. And these days, here's an article from the New York Times. You can see these meandered superconducting coplanar waveguide resonators that are very much like the kind that Rob Scholkopf had used for his demonstration. So now returning to the topic of detectors, okay, here you can see a nice photograph of a detector array with a transmission line snaking its way past all of the pixels. There's some 400 pixels in this array, and we use this kind of array to make an instrument that you see photographed here. This called Mako. Here you see the detector array being read out. We took this. Let me just show you a few more details. The resonators now you can see are a little different. The area of the absorber has been shrunk to make it more sensitive. The capacitor has been made larger to keep the resonance frequency low. We're using microlens arrays to illuminate these small absorbers efficiently. And then with this instrument, we went to this telescope that Bob Layton designed on Mauna Kea, the Caltech Submillimeter Observatory, and we used it to demonstrate these detector rays, as you can see here. This is an image of the Sagittarius B2 molecular cloud near the center of our galaxy. See very nicely the NM and S cores. These detectors are also being used to do visible light astronomy. This is work by Ben Mazin, another former student at UC Santa Barbara, and he's now in the process of building instruments using fairly large arrays, 10,000 pixels or so, you can see pictured here. And here's an example of one of the instruments that he's building. He's building instruments for Palomar, for the Subaru telescope in Hawaii, I think also for a NASA balloon project. And these detectors, like the X-ray detector, respond to individual optical photons and give you a pulse whose size tells you the energy of that visible photon. And so you can make an array which counts photons and also registers their energies individually. His inductors, as you can see, are much smaller. His capacitors are large, and again, he's using a microlens array to illuminate these detectors. I'm going to skip this. I think I'm out of time. There's an interesting story that has to do with the physics of the noise in these devices, which took us quite a while to unravel. But we've unraveled it. We understand it. So I think I'm going to pass right over this and save it for questions. I'll simply say at this point that there are now a number of instruments that are using this technology. This is another instrument that our group built for the submillimeter observatory, a longer wavelength instrument. There's the NICA and NICA 2 cameras, which are being deployed. The NICA 2 has now been commissioned on the 30-meter telescope, millimeter telescope in Spain. Here's a photograph of the NICA 2 cryostat. It's quite large, as you can see. There's another instrument, which is for the Apex 12-meter telescope in Chile, which is interesting due to a very high detector count. I think it's the largest to date for this technology, some 25,000 detectors in the arrays. There's work that's going on in the U.S. for a balloon project called BLAST. It's a far infrared polarimeter. They're in the process of, I should say they were in the process of preparing for their first flight when their cryostat unfortunately blew up in the lab. So they have at least a 1 or 2 year setback. This happened fairly recently. And in comparison to the kinds of arrays that were used on Herschel Spire, the kinds of arrays that are being used on this balloon project, BLAST, are, as you can see here, some 5 times larger. So it's a big step up in terms of capability. So I think I will, at this point, go to the end. There's a few things I wanted to say about what's happening at NASA with respect to this detector technology. There was a activity that I participated in thinking about the future of NASA missions over the next 30 years. One of the ideas that was mentioned in this report was a large far infrared mission. This concept is now being studied by NASA. It's known as the Origins Space Telescope. And the idea is to have a fairly sizable telescope which is cooled to 4 Kelvin. This is not entirely dissimilar to the Millimetron project in Russia, with some, I think, important differences. But you can see the opportunity. Herschel was only cooled to about 80 Kelvin, and so there still is quite a lot of thermal background that detectors see. If you could cool the telescope to 4 Kelvin, that background becomes very much smaller and the sensitivity goes way up. The Webb Space Telescope really will only work out to not quite 30 microns, and so we're talking about exploring this region at longer wavelengths with very high sensitivity. And one of the major issues for this project are the detectors. It's how do you achieve the sensitivities required either for imaging or spectroscopy. You're talking about noise equivalent powers that are very small in the 10 to the minus 19 to 10 to the minus 20 range. At the same time, we need very large detector counts, many tens of thousands, if not hundreds of thousands of detectors. And we're looking to develop this kind of capability using kinetic inductance detectors. There's very nice work that has been done in the Netherlands. They've reached this few times 10 to the minus 19 watts per root hertz sensitivity with arrays at about 1,000 pixels total. You can see some images from that work. It's very high quality work. But nonetheless, we have a real challenge. If you look at the sensitivity and you look at the number of pixels, this is, I think, probably the closest demonstration, and we'd really like to get up to this zone. So we still have a fair bit of work to do. So at this point, I think I will end. I will simply show you my summary, and I'll let you read those, and I'd be happy to take questions.
Time for questions.
I feel bad to be the one to ask questions because I have at least several. But the first question is, do you actually see the MKIDs are going to get this, deployed in the major CMB experiments? Right. I mean, there's an issue of timing and inertia in the system. Right? So
yeah, that's right.
What's your prognosis on what's going to happen in the next?
So the CMB experiments to date have been deploying instruments with a few thousand detectors. And at that scale, the existing TES technology works. It's maybe a little painful to build those instruments, but it's still quite feasible to do that. The largest instrument that's been built with TES detectors to date is the Scuba 2 submillimeter camera on the JCMT, which has a grand total of 10,000 pixels split between two arrays, and really it's the 850 micron array with 5,000 pixels that sees the most work. Getting far beyond that scale, I think, is going to be a significant challenge for the TES technology. The CMB stage 4 concepts that are being discussed, I don't know what the exact detector counts that people are thinking of, but I've heard numbers that are an order of magnitude or more larger in the 100,000 range. I think at that level, the TES technology is really going to struggle. And I think many people in the community see this. There's some who think that simply a very disciplined, organized, industrial approach to the TES will get them there. There are others who really are having qualms and are thinking that other ideas are needed. So I think it remains to be seen how all that will play out. But it's really when you reach that kind of scale that I think the multiplexing advantage of the kinetic inductance detectors really starts to become extremely important. And I should say that there's a variety of there are a variety of options here. There are hybrid concepts that take some features from the TES bolometer world and combine them with the kinetic inductance detectors. An example is to replace the transition sensor thermometer with the superconducting resonator. And so instead of using the resonator essentially as the detector absorbing photons directly in the resonator, you're simply using the temperature dependence of the inductance to sense temperature. And that has some attractive aspects to it. It's less of a drastic change. I think some of the CMB groups may be more comfortable with taking that step as opposed to taking the full leap into kinetic inductance detectors. So we'll see. I'll also say at the same time, there's been very nice work done showing that the kinetic inductance detectors could do quite a nice job on CMB measurements. So I think it's entirely possible that you could use them.
Okay. Well, my assessment was it's a difficult transition right now because the field is wedded to a certain approach. Even if it doesn't mean going industrial and even building 10 times as many dishes as you have actually had to make. But we'll see what happens.
I think you're right. I think that there is in all of these things, the main issue is how do you get to your ultimate science goal with the least with maybe the best way to put it is the highest probability of success. And having a technology that you used before at a smaller scale gives you a lot of confidence. At the same time, if there's a serious challenge in scaling it up, that could ultimately lead your experiment not to succeed. So it's a hard calculation.
Okay, so then I had a second question. And that is, you showed at the beginning there's a problem about using these detectors for devices well above the band gap. And yet you talked about Mazen's, using them for optical and X-rays, and Mazen's design, which fills a very small fraction of the focal plane. What are the fundamental limitations you see for what kind of sensitivity you get?
Yeah.
Right. So, because if you're doing the large-scale structure survey, you would love to have a full focal plane that gave you R equals 10, not R equals 10, R equals 100, and you just do your target survey and get the redshifts, and you just do a few devices to train your AI to use the whole survey.
Right. Yeah. To begin with, I don't think I stated there's a problem with using these detectors far above the band gap. I stated that you can use them at any photon energy which exceeds the band gap. You can make a detector.
But in order to get the energy resolution, you've got to actually convert them all into
yeah. So there's the issue of energy resolution, which has to do with the statistics of the essentially the number of Cooper pairs that you end up breaking. If you really had a truly isolated system, there would be zero fluctuation because you have energy conservation. The number of Cooper pairs that are broken has to account for all of the energy. But what happens in practice is that some of that energy goes into phonons. Some of that phonon energy can escape from the superconductor into the substrate. And a particularly problematic issue would be if there's a hot phonon that escapes that carries away significant energy. So if you have hot phonons that escape, that will lead to significantly larger fluctuations in the energy that remains in the superconductor. So that's one of the issues to think about, to look at. There's been some work, I think particularly done at Cambridge in Stafford Withington's group, actually simulating in detail what happens with the cascade of energy as that photon is absorbed and is down converted and pairs are being broken. But ultimately the issue is, can you identify what some of the limitations are to the energy resolution that people like Ben Mazin are seeing? And B is, if you can identify them, can you find ways to improve it? I'm pretty optimistic that you should be able to have fairly substantial improvements simply because nobody has really focused their energy on this topic. Ben's group has been primarily focused on getting first-generation instruments out into the field without really digging deeply into the physics of what's going on in terms of the energy resolution. So I think there's a big opportunity to do a lot better, and it simply is going to require time and energy to go look at those issues.
Okay, so let's continue this discussion during this discussion session because we don't have time. We have to move to the next speaker. Let's
Okay,
our speaker
thank you.
again. It's excellent. So our next speaker is Osamu Tajima, and he will talk about the Front Bird project.
Cool. I have to give you this.
It's not kind of. No. What's happened? Okay. Oh. No. Right. Okay, let me talk about this title, Groundbird Kids Meets Cosmic Inflation. My name is Osam Tajima. Actually, I recently moved to Kyoto University from KK. Okay, let me briefly introduce about what is groundbird hereafter GB. So groundbird is a radio telescope using a kinetic inductance detector, also called KITS. And our observation target is CMB polarization. In particular, BMOS patterns are smoking gun evidence for the cosmic inflation. It sounds quite exciting topic, and maybe as you know, CMB is a remnant of Big Bang thermal radiation. Of course, the era of Big Bang, so CMB was ultra high energy thermal radiation at that moment. But with the expansion of our universe, so now CMB is observed as a ultra cold radiation of 2.7 Kelvin. So we can detect the CMB as a faint millimeter wave. So therefore we need a high sensitive detector, so-called for example, superconducting detectors. So this is just an image. So if we see the sky in millimeter wavelengths, so we should see such a CMB patterns, of course, behind the galaxy. And actually, the frontier in the last 2 decades for the CMB study is temperature entropy. So I mean, unpolarized fluctuation. It's 0.01% level of fluctuation. So right today, with a combination of both satellites and big ground-based telescope, so we measure this isotropy very precisely. One of the important achievement based on this measurement is we determine the energy budget in the universe with 1% precision right now. So as you know, our universe is dominated by dark energy, and matter is dominated by dark matters. And now, today, the CMB frontier topics are polarization patterns. So there are 2 types of polarization patterns. So one is E-modes, which is the even parity patterns. The another one is a B-modes picture odd parity patterns. So frankly speaking, these E-modes patterns are kind of areas of temperature anisotropy. On the other hand, so this asymmetric B-modes pattern, so for example, more than degree scale patterns, which is evidence for the cosmic inflation. So again, inflation is a frontier topic in the cosmology. And before the Big Bang era, so we believe, so there was an accelerated expansion of space time metric, and this inflation generates such a Big Bang era high density and high temperature state. And also the generic prediction of the inflation is a generation of gravitational waves. So since we believe this is the first gravitational waves in our universe, so it is called primordial gravitational waves, so-called PGW. And these primordial gravitational waves have been presented anytime, anywhere in our universe. And actually, the CMB, in particular, beam modes, this asymmetric pattern is the best proved to measure, to detect these primordial gravitational waves. So you may, actually, you may wonder about the difference, another type of gravitational waves experiments by using an interferometer like a LIGO experiment. So our approach is actually the look at this beam modes pattern on the wave surface of primordial gravitational waves. So CMB polarization is a reflected pattern. So that's why we observe the reflected pattern on this surface. And on the other hand, for the case of laser interferometer experiments, so just imagine they put the two yachts on the wave surface, and they measure each position by using a laser interferometry technique. So if we say one word, so their approach is a fuse wave motion. So that's why the difference of approach is look at it or feel it. So by the way, long time ago, so far from our galaxy, so one of the great master said, don't think, feel it. So it sounds feels better than look at it, but look at his hand. You know, here, there's a laser. So at that moment, laser was his own technology. So right now, we have a technology to look at the millimeter wave. So if he has a technology for the millimeter wave sensing, so for that case, I believe he said, look at it to avoid the wall. So they don't need any laser light survey at all. So anyhow, there's a big benefits of look at it. So we observe such a asymmetric pattern. This is just an image anyway. So we characterize these observation patterns in a Fourier space. In Fourier space, we can characterize the angular scale of the signal. So for the case of primordial beams, beams from the primordial gravitational waves, we have such a two-bump structure. So this degree scale structure corresponds to the recombination error, and the more than 10 degrees structure corresponds to the reionization error. So if we can observe these two bump structure, so this is a strong evidence of the primordial gravitational waves has been exist anytime, anywhere in our universe. And actually, as the small angular scale, sub-degree scale, so there is another type of beam mode. I don't explain detail about it, but so this small angular scale beam mode is generated by the gravitational lens effect by the galaxy clusters. So if you Google the gravitational lens, you can see such a picture. And so this indicates the gravitational lens effect rotates the axis of polarization. So that's why the E-modes as a recombination error can be observed as a lensing beam mode at sub-degree scale. So we can distinguish lensing beam modes or primordial beam modes if we characterize the angular scale. So this beam mode is sub-degree scale, and the primordial one is a degree or larger angular scale. Okay, so right now, observation of beam modes is in progress. There are several, I think, more experiments. So for example, polar bear and octopus, they are observing CMB at the Atacama Desert in Chile, and at the South Pole, so biceps sleeves and Kekkar experiments, and also SPT telescope, they are observing CMB, and actually, last 4 years, there were significant progress for the BMOS measurement. So today, we detect the finite signal for the lensing BMOS like this. And on the other hand, we haven't observed the primordial BMOS yet, but right now, its limit is very stringent. So I believe we will observe this primordial BMOS soon. So under this situation, so Randward should aims unique science topic which is not covered by other ground-based telescopes. So one of them is a very large angular scale observation. And of course, a large angular scale observation is a target of the future satellite mission, for example, Lightbird experiment. And but we would like to prior to the future mission. So again, this is a power spectrum as a function of multiple, inverse of angular scale. The coverage of the ground-based, majority of ground-based experiment is degree scale and sub-degree scale, and the targets of the future satellite mission is a very large angular scale. So we would like to go somewhere around between those two strategies. And this strategy actually can catch the both bump structure from the primordial BMOS. So this strategy has a potential, potential to catch a dark horse scenario. I don't know this dark horse scenario is good or bad, but anyway, so one of the exotic model for the cyclic universe predicts the spectrum shape can be varies drastically. So if there is a universe before our universe, so we have potential to catch such a dark horse scenario. So, right. So let's move on the overview of ground-bird instrument. So again, we are CMB telescope like this. So the signal comes from the top direction like this, and by using cross-diagonal dual reflector mirrors, so we focus the signal to the focal plane. So the focal plane detector is maintained at 250 VK. And so to mitigate the effects of atmospheric fluctuation, we employ the super high-speed scan modulation. So roughly speaking, this scan speed is a factor 100 faster than the ordinary ground-based telescope. So this scan strategy is actually similar to the satellite scan, so-called low Earth orbit scan. So so with a combination of rotation scan and Earth rotation, so in a day we can cover, roughly speaking, half of the full sky. And our ambition is actually the all sky survey from the ground. If we have two ground-bird telescope at North Hemisphere and South Hemisphere, so for that case, we can cover the all sky effectively. And towards this ambition, so at first we plan to start the North Hemisphere observation next year. So our observation site at the north side is Canary Island. So it's Canary Islands located at the north-south side of Africa. And here the altitude is 2,400 meters. So but the level of clouds is very low, less than the 1,500 meters. So we always see a clear sky above the cloud. So, and right now, our observation site in under preparation. So both the political way and the actual way. So we did a sign for the MOU 2 years ago, and based on the agreements, ISC prepared our foundation, and in the future this is just an image. We will install our telescope like this. And another key feature of ground board is we employ the KICS array. As Jonas mentioned, the principle of KICS is very simple. We have a superconducting resonator, and if the signal comes from the antenna to here, so we can detect the signal as a change of the frequency resonant condition. And one of the big benefits of the kits is we can easily to increase the number of detector, which means that we can easily increase the statistics. So that's a good benefit. And so of course there is a simple reason why we use the kits. So because our scan speed is very, very fast, so we have to sample our sampling rate of the signal should be fast. And for the fast sampling rate, so we need a relatively fast response detector. So KICS has a relatively fast time response. So this fast time response is well matched with ground board's high speed scan. That's the reason. So anyway, so we use KICS inside of the telescope. So to maintain the cold temperature, we need a cold optics. So we maintain all the optics components as a 4 Kelvin temperature. So this is just a slideshow about the construction, how to construct this 4K shell. So at first we prepare the 4K shell base plate and 50K base plate. So they are isolated by using carbon fibers. So it has a good thermal isolation and good mechanical strength. Then we construct the mirrors, optics, and focal plane on top of this plate, and we have a 4K shell cover, 50K shell cover, and the whole the system is hung under the 300K top plate. Then after we put some multi-layer inflation, we insert our receiver system into the such a big cryostat. And actually, the focal plane support structure is more difficult. So even though the detector is surrounded by 4K temperature, actually we achieve 3.7K, but so we have to isolate from 4K to 0.25K temperature, and finally we made such a support structure, and we have 250 mK stage, 350 mK stage, and 4K support structure. So they are supported and isolated by using a Kevlar strings. So we control the tension of Kevlar strings by using a spring, and so we worry about, so it looks very, very fragile. But we did test for the mechanical strength. So we prepare such a test jig, and we did a test for the mechanical strength, and so we clear our requirement. And also we did test for the thermal stress. So we put this jig into the liquid nitrogen and make sure so it is good enough. And finally, so human use this jigs. So finally we did a human stress test. So here there is a jig, and they tested, and so we clear such a very strict test. Okay, then we put some focal plane supports like this, and we achieved 230 mK temperature. Okay, so let's move on the focal plane. So this is a prototype. We only have right now only have a single wafer, but our final configuration of the focal plane is like this. We have home coupled pitch array. So we have 7 hexagons, and we have 2 frequency bands. So one is a 145 gigahertz for the semi observation, and 220 gigahertz for the dust observation. So this is a design of corrugated foam. We designed by using a HFSS simulator, and we make this corrugated foam by using the direct machining by 3 steps. So this is acrylic, so not metal. This is just demonstration. So first step, we make such a through hole, then we make a taper structure. Then finally, by using such a special shape drill, or we make a corrugated structure like this. And so this is a prototype, a first prototype array made by direct machining. So it looks nice. So going to the detector design. The design of the 145 gigahertz cage array is like this. On the 3-inch wafer, we have 55 pixels. So each pixel has 2 M kits. So in total, we have 110 kits on the single wafer. And this is an enlarged design for the single pixel. So we have antenna here, and this direction polarization is transmitted to the M case like this path, and this direction is transmitted to this M case. And in the design stage, so we designed for each component by using a various simulator. For the case of antenna coupling, we use HFSS or CSP simulator, and for the case of, for example, transmittance line structure, we use a Sonnet simulator. And we linked simulation results by using an ADS simulator, so which means that we can effectively perform the end-to-end simulation. This is just one example for the horn and antenna coupling. So we defined the port like this, and for this direction polarization, so port 2 and 3 picked up the signal for the opposite phase, and for this direction is picked up by port 4 and 5, and there is a crosstalk mode. And we suppress this crosstalk mode by using this structure, 180-degree hybrid. And this hybrid structure can separate the signal and the crosstalk mode to the opposite direction. So we can suppress the effect of the crosstalk mode. And then finally, end-to-end simulation results is like this. So we obtain wide bandwidth, having a good transmittance. And for the crosstalk, separation of crosstalk, so here is the worst region. So even for that, so separation level is minus 40 dB level, so which means the crosstalk level is 0.001, less than 0.001%. So it's good enough for us. So for the detector fabrication, so because Japan has good technology for the hybrid, so we employ the hybrid fabrication approach. So what I mean the hybrid is, so we use 2 types of photolithography technique. One is aligner, and another one is a stepper. So aligner can make a photolithography for the full array with a different full array, and on the other hand, and stepper can do a photography for the small region, but it's very precise. So the feed line and kids resonator line design, they are different for each pixel. So that's why, so there's a big benefit to use a liner. And on the other hand, for the antenna structure, so they are identical, but so we have to make a pattern very precisely. So we use both technique and with a common alignment marker, and we finally processed such a prototype MKS array like this. And this is one of the pixel. So we have antenna and transmitters line hybrid, and here is MKS. And this region is fabricated by using a liner, and this region is fabricated by using a stepper. And so to give the signal, so at least we have 110 detectors. At least we need a 110 multiplexing factor without any dead time for the readout. So we actually made our own front-end electronics. So it consists with two parts. One is the analog interface, and another one is a digital processing. So this DAAD interface board is called actually RARE. So of course there is a meaning. So RARE is high-speed electronics analog interface, probably. But the reason why we choose the name of RARE is one of the grandmas. That's the reason. So anyway, so based on these two combination, so thus far we achieved a dead timeless readout at 1 kilo SPS. So this is a requirement for the grandfather experiment, and we also achieved 120 multiplexing factor in a 200 megahertz bandwidth. So there are some option functions. Sampling speed is, of course, can be set up to 200 megahertz. And we also have a trigger function. It's useful. So this is just a demonstration of the role of measurements of the MK. So this is a PSD as a function of the frequency. So we can measure such a cutoff. So this cutoff indicates the finite lifetime of the quasi-particle. So it is useful to measure the quasi-particle lifetime. And there's another way to measure the quasi-particle lifetime is by using a cosmic ray. So if we can measure the cosmic ray events pulse shape like this, we can measure the time constant of the detector. So this trigger function is very, very useful to measure the quasi-particle lifetime. So recently we employed we integrate our prototype detectors, electronics, and our main cryogenic telescope, and we are doing an end-to-end test right now. So here is actually a telescope aperture. So this guy is just open and close aperture. So which means so we insert the 300K signal and close the signal like this. So you can see. So it should be here is no. So this, oh, okay, it's worked. So you can see such a modulation like this. So of course we are doing a serious test again about the polarization signal. So here it's hard to see. Here is a signal generator. It's polarized signal. And we modulate the axis of polarization by using a half-wave plate. So if we rotate the half-wave plate, polarization axis is modulated. So we observe such a cosine square response property. So this is a response for X antenna. And for the case of Y antenna, the phase is opposite, right? So which means we measure the polarization signal property. This is a good achievement. So So we can measure the polarization, but before start the observation, so we need to influence a good magnetic fields, because our rotations can modulate the geomagnetic fields. So this is just a demonstration. So by using a small cryostat, so we demonstrate the response as a function of rotation. This is before the installation of the magnetic field. So definitely there is an effect, large effect. But after the after the installation of magnetic field, so we can eliminate this effect. And we need a good design for the large cryostat. And we designed magnetic field by using simulation. And we check the reliability of the simulation. So we use, again, small cryostat system inside kits. And we prepare the solenoid core and we make a magnetic field. So this is a response of a case as a function of magnetic field. So without field, definitely there is effect, but if we install the magnetic field, so we can demonstrate and we can evaluate the impact of the simulation like this. So, and based on this small system measurement, we confirmed the requirement of 40 dB shielding is reasonable. And for the main cryostat stuff, so we finally define our magnetic shields. So we install the 9 layers of thin magnetic shield at each layer at 300K, 50K, and 4K, like this. And we can suppress the effect of the geomagnetic field around the level of 45 dB. So we would like to demonstrate the impact of magnetic field with a full integrated system. We haven't done yet, but they are working hard like this. So please stay tuned. Okay, so today I talk about the groundwater, but our groundwater is not only project in Japan. So we are endorsing Marsh project. In addition to groundwater, we are doing a Simon's Array and Simon's Observatory, and also future mission, a satellite mission, LightWorld. So if you are interested in, let's collaborate together. So in particular, recently I'm searching a good postdoc candidate for the Simon's Observatory. If you are interested in, or if you know a good candidate, please let me know. Okay, so maybe I have 3 more minutes. Okay, so let me show some byproducts of the groundwater technologies. Since there's not much time, so please ask me about the detail during the coffee break or during the banquet. So one byproduct is water vapor monitor for the tornado and the sudden heavy rain forecast. So based on the groundwater technology, we developed the next generation water vapor monitor. Its name is Kumodes. Kumodes can measure the water vapor. So actually, before the storm, so there is such a tall clouds. So today's weather monitor can detect can monitor the clouds, but they cannot monitor the water vapor at all. So that's why. So if we have many Kumodes in the world, so we can monitor the local increase of the water vapor. For that case, there is a possibility to make a forecast of storms 1 hour before it happens. So it's very important technology. And another byproduct is a direct search for hidden photon called dark matter. So actually, this is a byproduct of Kumo desu. So I mean a byproduct of ground bird. So anyhow, so this is actually the Kumo desu. A spectrometer in millimeter waves, and if we put the metal mirror in front of the aperture, so we can search the hidden photon called dark matter. So we already did the test search as a small mass region, and we already have a preliminary results, but it's already world best search results. So we can easily to increase the mass range if we take more time. All right. So let me summarize my talk. Ground boat is a CMB telescope. So our target is cosmic inflation, and to measure the faint beam modes, so we use MKs. And now integration and end-to-end tests are going on, and shipping to Canary Islands is planned early next year. So we will do a CMB observation there. All right, that is all. Thank you.
Thank you very much. So we have time for questions.
What are you going to deploy the IAC?
Thank you for a very nice. Thank you for a very nice talk. I was curious about your measurements with respect to magnetic field. You're showing a linear variation of phase with field, whereas it should be quadratic, which leads me to think that there may be a built-in field that's stronger. So the minimum is displaced somewhere.
All right. So that's why we would like to demonstrate with the real system as soon as possible to make sure it's really good or not.
Because you would get a very different estimate for the amount of shielding required if you have the assumption that it's quadratic instead of linear. It's much easier to shield if it's quadratic.
Right.
As it should be.
So what I was starting to ask was, you either I missed it or you didn't say quite clearly. What is your estimated schedule for deploying in the Canaries versus going to Chile?
No. So currently we only funded for the North Hemisphere observation. So right now we don't have any plan. We don't have any concrete plan to the South Hemisphere yet. And for the Canary case, so our baseline plan to go Canary early next year, 2018, and start commissioning as soon as possible.
And did you test that? You had the claim that the sky was always clear. But my experience was the sky wasn't always clear. That the IAC advertises it that way, or felt, because they want people to come. But in reality, we actually got water in our equipment from rainstorms. So there's the issue of what kind of protection you have to have.
All right. So first of all, so no, I think no one observes at 150 gigahertz at Canary Islands. So that's what is one of the risk. I understand. So that's the reason we want to start the observation as soon as possible. So we want to make sure at the early stage.
I have a really elementary question. Could you just go back and describe again how the polarization works? And do I understand that there's a separate line to each? There's a separate line for each polarization?
Do you mean a design of antenna?
Yes, in each pixel. Okay. How does the polarization work?
Okay. This one. Yeah. Okay. So the polarization picked up by these two planar OMTs. So so phase this direction and this direction is opposite. And so this is a
OMT stands for
sorry.
OMT stands for
Also wanna I can't remember, but so it's antenna, kind of antenna. But we picked up the opposite phase. So the length of the transmitter's line is half wavelength difference. So that's why we can combine the both directions here. And for the case of crosstalk mode, so they are in phase. So that's why the crosstalk mode goes to the opposite direction. So that's the logic. We can suppress a crosstalk mode.
what's the frequency band
For MKIT or CME?
for the whole experiment? What?
Okay, so to observe the sky, so we employ the two frequency bands. One is 145 gigahertz and 220 gigahertz. And for the resonator, so we use the frequency bands around the 5 gigahertz.
So, what's the advantage of the kids if you're saying to narrow frequency bands? Right, I think of kids as doing the frequency multiplexing.
Yes,
It doesn't
yes.
sound like you're increasing the bandwidth over what you just get with TES detectors.
Oh, so it's a different issue. So it is easy to increase the number of detector, but to increase the number of frequency bands is a different issue. So for example, if we want to go the higher frequency bands, so we have to design the small, fine structure for the transmitters. And one of the disadvantage for the case of aluminum MKs, for that case, minimum frequency band is somewhere around 80 gigahertz. And if we want to go to the lower frequency, we have to change the material. For example, Jonas mentioned TIN. And of course, we need a lower temperature.
Probably you already somewhat presented, but what is the upper bound of the R if we assume you actually completely clean the lensing component? And also my second question is that how much you can improve the time you actually launch the light bulb?
I'll say first question is what is the target range for R?
Upper bound of the R.
Okay, so for the first ground band case, so our primary target is a level of R 0.016, something like that.
So you assume you clean all the lensing contribution.
So our coverage is large angular scale, so we are free from the lensing.
Yeah, so you don't have to. So kind of even you can see the reionization bump. Yeah.
Yes. And another target is actually the large angular scale EMOS. So we can measure the optical depth. So that's the important parameter to determine the neutrino mass, for example.
Do we have more questions? If not, let's thank the speaker. And we have an announcement to make, right?
All right, two announcements. One is the poster boards have been put up at the coffee break area. So if you have posters to present, please go ahead and put them up at the beginning of the coffee break. And during the coffee break, everyone can take a look at them. We have a dedicated poster session tonight at 5:45 to 6:45. So before the banquet, before the bus comes to take us to the banquet tonight. So whoever's presenting a poster, please stand by your poster at that time so that people who have questions can contact you. And Bruce will talk about the detector discussion.
So as a general guideline to the detector discussion, which is scheduled for 50 minutes, I'd like to have about 30 minutes of talking about the future of these detectors, and then about 20 minutes for observers and users of instruments to ask the detector specialists what they want and how they might get it. Those are just general guidelines, of course.
Okay. And
Okay, now we have a coffee break and we will be back exactly at 11.